Today, we're diving into how the discovery of the electron and quantum theory are deeply connected. The electron's discovery laid the foundation for quantum physics, and quantum theory, in turn, helped explain the electron's unique behavior. The discovery of the electron 1897, J. Thomson. Let's start with J. Thomson's groundbreaking discovery. In 1897, while experimenting with cathode rays, Thomson found that these rays were made of tiny particles much smaller than atoms. He had discovered the electron, a negatively charged particle. This meant that the atom wasn't the smallest building block of matter, as people had thought. It opened the door to a new understanding of atomic structure. Thomson's discovery raised an important question: how are these electrons arranged within atoms? To answer that, we needed a new theory: the connection between quantum theory and electrons. 1. Bohr's atomic model. 1913. Enter Niels Bohr. In 1913, Bohr proposed that electrons orbit the nucleus in specific, quantized orbits. Electrons can't just exist anywhere, they can only occupy certain orbits. Bohr's model also explained that when an electron absorbs or emits energy, it jumps between these fixed orbits, producing the spectral lines we observe. This was the first major step toward understanding that electron behavior could only be explained using quantum theory, not classical physics. 2. Wave-particle duality. As quantum theory developed, Louis de Broglie introduced a mind-blowing concept: wave-particle duality. He suggested that electrons aren't just particles, they also behave like waves. This means electrons can show wave-like phenomena, such as interference and diffraction. The idea that something could be both a wave and a particle was revolutionary and became a core part of quantum mechanics. 3. Heisenberg's uncertainty principle. Then came Werner Heisenberg's uncertainty principle. According to this principle, we can't measure an electron's position and momentum, how fast and in what direction it's moving at the same time, with perfect accuracy. The more precisely we know one, the less precisely we can know the other. This shook the classical idea that particles like electrons could follow a predictable path. Instead, quantum mechanics told us that electron behavior is best described in terms of probabilities. Conclusion: the discovery of the electron forced scientists to rethink how atoms work, and it set the stage for the rise of quantum theory. Electrons don't behave like tiny planets orbiting the sun, as classical physics might suggest. Instead, their behavior is governed by quantum rules. They occupy discrete energy levels, they act like both particles and waves, and we can't predict their exact path with certainty. Without the electron's discovery, the development of quantum mechanics might never have happened, and our understanding of the universe would look very different today.